So with this problem, we want to maintain a voltage difference of 5,000 volts between two plates. So we've got two plates like this, and because they're parallel plates, we've got a constant electric field between them. And in one of these situations, we've got quartz between the plates, which has a dielectric constant of 4.3 and a breakdown threshold of 8 times 10 to the 6 volts per meter. So this is the maximum electric field it can withstand. And we've also got barium titanate with kappa is equal to 1200 and a breakdown threshold of 8 times 10 to the 7 volts per meter. And we're asked for these two cases, if these are in between the plates, what's the minimum distance that the separation between the plates can be. So we know that the potential difference is given by minus E dot ds. Now in this case, we're interested in the absolute value of this. So we can just get rid of this negative sign. And we know that the electric field between the plates is constant and that the distance between them is d. So we're going from 0 to d. And when we do this, we just get ED is the potential difference between the two plates. So if we want to know what the minimum D is going to be, then that'll be when we've got the maximum value for E, given that we know our potential difference. So we can write D min is going to be equal to delta V over E max. And so for quartz, this will be 5,000 divided by 8 times 10 to the 6. And when we solve that, we get 6.25 times 10 to the minus 4 meters. So we should really just give this to one significant figure because we only knew the breakdown threshold to one significant figure. So this is 6 times 10 to the minus 4 meters. And then that was for quartz. And now we want to do barium titanate. And so D min will be equal to 5,000 over 8 times 10 to the 7. So this will be 10 times smaller than this. So 6.25 times 10 to the minus 5 meters, which is 6 times 10 to the minus 5 meters. And then in the final part, we're asked for the ratio of the maximum charge on quartz to the maximum charge on the barium titanate. So for this one, we'll need an expression for what the charge is. So we know that the potential difference between the plates is given by ED. Then hopefully you remember that when we've got parallel plates like this, the electric field is given by sigma over epsilon naught. Only in this case, we've got a dielectric in here. So we replace epsilon naught with kappa epsilon naught. And because sigma's Q on A, this is equal to Q over A kappa epsilon naught. So we can now substitute this in for E down here. So this is equal to Q, and we've still got the D here, and we're dividing by A kappa epsilon naught. And what we're interested in finding is Q. So let's rearrange this and make Q the subject. So Q is equal to the potential difference times A kappa epsilon naught, and then we'll need to divide by D. And what we're trying to find is the maximum Q. So you can see from this equation that Q is going to be a maximum when D is a minimum, and we worked out the minimum distances here. So to get the ratio of the quartz on the barium titanate, we'll need to substitute in here. So we've got the potential difference for quartz times A times kappa for quartz times epsilon naught divided by D min for quartz, which we calculated up here, and then we divide by the same for the barium titanate. But the potential difference is the same for both of them. We kept it at 5,000. The area of the plates is the same, epsilon naught is the same, and so we've just left with our kappas and our d mins. So we can write this as kappa q times d min for the barium titanate divided by kappa for barium titanate times d min for the quartz. And substituting in, we've got that kappa for the quartz is equal to 4.3 and d min for the barium titanate was 6 times 10 to the minus 5. And then kappa for the barium titanate was enormous. It was 1,200. And then d min for the quartz was 6 times 10 to the minus 4, which is 3.6 times 10 to the minus 4, which to one significant figure we can write as 4 times 10 to the minus 4.